Hello. So, in the previous lecture or recording, we defined a cluster point for a subset of real numbers. So recall, if you have a set of real numbers, a subset of the real numbers A, and you have a number C, then C is a cluster point of A if for any choice of positive delta, there is a neighborhood around C, or a distance around C, so that inside of that neighborhood, there's an element of A different than C. And these are two varying ways to interpret that. There's the absolute value distance on the real number line definition, or equivalently, the delta neighborhood definition, where you can think of little balls around C that intersect A at a point different than C. So these are cluster points. And now we're going to prove one theorem about how sequences and cluster points interact on the real number line. So this theorem states that a number C is a cluster point of a set A if and only if, so it's biconditional, if and only if there is a sequence of elements in A that converges to C and none of those elements equal C. Okay, so this is a characterization of cluster points for a set A. Okay, so it's a biconditional statement, so we have to prove two things. So let's go ahead and get started. Proof. Okay, so first we're going to suppose that C is a cluster point of A, and then show that there is a sequence that converges to C that is different than C. So the way that I'm immediately thinking is that we're going to construct such a sequence. So maybe first suppose C is a cluster point of A. Okay. Okay, so now we need to build a sequence that converges to C that's different than C at each term. So the only thing we can really work with is this definition. So we know that if C is a cluster point of A, right, then for any choice of delta, there's a little neighborhood around C that contains an element different than A. If we can make these neighborhoods get smaller and smaller and smaller, we can force those elements that are guaranteed to be in these sets, by definition, we can force them to get closer and closer and converge to C. Okay, so I think that's the idea, the approach, is to take smaller and smaller delta neighborhoods around C and pick an element from each of them so that as we get smaller, we go to C. Now, the only trick is to somehow pick this in terms of something that we can take a limiting value of, for example, N. So, and we can always use 1 over N. We've used this before in analysis, so let's go ahead and try to do this. So we're going to use this definition. So by definition, so for every choice of delta greater than 0, we can find a point different than C that's within that distance to it and also contain a name. So by definition, there is a number. I'm going to call it A sub n in A with A sub n not equal to C, so that the distance from A sub n to C is at most 1 over n for all n that are natural numbers. So for all natural numbers n. Right, so this should match up with the definition. We just applied it. So this is like choosing our delta right here, right? That's our delta. So for any delta greater than 0, which this is greater than 0, there is an element in A sub n, call it, that's different than C, okay, so that the distance from that element to C is at most delta. This is a positive number for any choice of n, so this always has to hold. So look what we've done. So we can collect each of those terms in a sequence. So how can I word this? Then if we collect A sub n for each natural number n, we form a sequence. A sub n with A sub n not equal to C for each n. Okay, it's kind of jumbled for each n. And then also we know that as n goes to infinity, they converge. For each n, so that the limit of A sub n is equal to C. Okay, so this proves the first part of this biconditional statement, right? And again, it was constructed. We use the definition in terms of n instead of delta. We guarantee the existence of this for each choice of n. You just pick, form a sequence. And since this goes to 0, the distance goes to 0, it converges. Moreover, we guarantee that each instance of n, A sub n is not equal to C. Okay, we got it. So that's the first part. So now we have to prove the converse. So conversely, okay, we need to start from a sequence that converges to C, which is contained in A but never equals C. Start with that and then show that C must satisfy this definition or this definition. The same, they're equivalent, but like one of these things, whichever one is easier to write about and to kind of think about. So conversely, suppose there's a sequence A sub n is a sequence A sub n and a set difference C, right? So this is guaranteeing that when we're going in the converse that we have a sequence in there, but it doesn't equal C, okay, for any choice of n. Right, so there's a sequence A sub n in there, so that the limit of A sub n is equal to C. All right, so we're assuming this, and now we have to show that. Okay, so we need to show that for every choice of delta greater than 0, there's at least one element in the set that's within delta distance to C. Well, we can do that. It's almost like immediate, right? Because this limiting definition means that there's some index, once you get past that index, you're arbitrarily close to C, or within whatever choice of epsilon that you have. And since none of those terms equal C because of where it lives, then that's basically it. We have the definition. So let's see if we can piece it together. Okay, so then for delta greater than 0, so treat that like your epsilon. There exists some index. I'll call it k, which is dependent on delta, k delta, just some index. So that n greater than or equal to k delta implies that the distance from the sequence to C, the limit, is less than delta, right? Okay, this is for every n greater than that cutoff value, right? Okay, so now since this sequence lives in A set difference C, none of these A sub n is going to be equal to C. So maybe I should say that where no A sub n equals C. Okay. So that's basically the definition now, because we're guaranteed at least one. There's going to be infinite actually. Guaranteed at least one to satisfy that definition. Yeah, we can just like state this right here. So this implies that given a delta, there is a non-empty neighborhood around it. So that's, I'm trying to think of the best way to word it because it's there, it's true. Maybe like therefore there's a neighborhood because that's what it is. This is a non-empty neighborhood. That doesn't equal that, and that holds for every n greater than C. It's a non-empty that forms a delta neighborhood. That's it. So therefore, for each delta greater than 0, there is a delta neighborhood. What's the best way to word it? Because C is always in the delta neighborhood. So we could say yeah, there is a neighborhood, and I'll just say the definition. Therefore, for each delta greater than 0, there is a delta neighborhood of C that contains elements of A distinct from C. And then we're done. Hence, C is a cluster point of A. Done. Okay. I don't know why it took me so long to finish that proof because it was literally just that sentence, but that completes the proof. Okay, so we have now a nice characterization of cluster points. Not only does it satisfy this definition, but if you are a cluster point of some subset of real numbers, then there better be a sequence in that set that converges to the cluster point and doesn't equal that cluster point for any of the terms. Okay, so that would be it for this recording. Thank you for watching.